In this video, let's try to understand all about logarithms with respect to coding interviews, and the good news is that it is not much. So let's dive in over here. Now, whenever we say log n in coding, it's always log n to the base 2. So we typically shorten this and we're just saying log n, but it's always to the base 2. Now let's take an example. Log 16 to the base 2 is actually equal to 4. Now what does this mean? It means that 2 to the power 4 is equal to 16. So with this same thing in mind, let's try to think about log 8. So what would be log 8? Now if you want to find out log 8, we can rephrase this and we can say 2 to what power will give me 8. That's the same thing over here, right? 2 to the power 4, that was the answer over here, gave me this 16 over here. So instead of 16, I have 8 because I'm finding log 8. So 2 to what power will give me 8? And we know that 2 to the power 3 is equal to 8. Therefore, log 8 is equal to 3. So this is what we mean with log n. Now, the interesting thing about log n is that it's a very good time or space complexity, because let's take a look. Let's have a table over here, n and log n. Now let's take two values. Let n be 2 to the power 10, which is 1024, and let it be 2 to the power 20, which is 1,048,576. Now if we take log n in both the cases where n is this and this, right? So when n is 1024, log n is going to be equal to 10. And when n is equal to this value over here, log n is going to be equal to 20. Again, why is that so? Let's try to understand. So we are taking log 2 to the power 10. If you want to find this, this is nothing but 2 to what power will give me 2 to the power 10. And we know that 2 to the power 10 is giving me 2 to the power 10, right? So I'm just writing it in this manner to make it easy, but we could think of it like this also. Log 1024 is equal to what? Which means 2 to what power will give me 1024, which is 10 itself. So that's why over here we have 10, and similarly over here we have 20. So you can see that when n is increasing from 1024 to 1 million something, log n is just increasing from 10 to 20. So that's why you can say that log n is a very good time and space complexity. All right. Even in the graph which we discussed previously, if you notice, you can see that log n is increasing at a very slow space. So if this is constant, log n will be going something like this, very near to constant, if n is going somewhere like this. So that's why the reason for that is over here, right? You can see it's increasing at a very slow pace. So therefore, log n is a very good complexity. All right. So we have understood what log n is. We have understood how to calculate log n, right? For example, log 8 is nothing but 2 to what power is equal to 8, and that is equal to 3. Therefore, log 8 is equal to 3. Now, let's also get some intuition regarding algorithms where, let's say, the time complexity is log n. If you have an algorithm that cuts the input in half at every step, then you can say that that relationship is log n. Now, why is that so? Let's try to understand that. Let's say we have 8 elements and we are searching for some element. Now we will see this later when we discuss binary search, but let's say at every step we can eliminate half of the remaining input. So initially we start with 8 things to search through. Then after one step we only had to search through 4 more things. Then after one step we narrowed down to 2 things, and then we narrowed down to 1 thing. So we found it. So you can see we just had to do 3 checks over here. So the input size was 8 and we only had to do 3 operations. So you can say that over here, the number of operations is of the order of log n or log 8, because 3 is equal to log 8. So over here we have a relationship where the time complexity is of the order of log n. Now this is just to develop an intuition. We will see this in detail, especially in the question where we discuss binary search. Now another way in which you can think about a time complexity of log n is, if you double the input, you are only going to do 1 extra operation. So let's take the same example over here. We started out with 8 elements. Let's say we start out with 16 elements. So from 16, we eliminate half and we are left with 8. From 8, we eliminate half and we are left with 4. From 4, we eliminate half and we are left with 2. And then we find the thing, right? So we just have 1. So you can see we just have to do 4 operations over here. So we doubled the input from 8 to 16, but the number of operations only increased by 1, from 3 to 4 over here. Over here, log 16 is equal to 4. That's why this is another way of thinking about log n time complexity. And you will also come across that in many recursion based questions, the space complexity is going to be O of log n because space is going to be consumed in the call stack. Again, don't worry about this. We will see this in detail in the future part of this course.